Hello, hello, and welcome. This chapter we're going to look at equations, inequalities, and applications, and solving those things as well. But first I want to get through some basic terminology just to make sure we're on the same page. First I want to distinguish between an expression and an equation. An expression is just a number, like 7, or x plus 5, or 3x minus a half. Anything like this. It could have multiple variables in it, even x plus y, whatever. It's just but all of these four things represent numbers. They're essentially the nouns of our in algebra, in an algebraic statement. Now the algebraic statements themselves are essentially equations. They're the sentences. There are also inequalities, which are also sentences. Both of these are sentences, and I'll show you why here. So an equation has an equal sign in it. X equals 7. So we've got two expressions: the expression x, which is a number, and the expression 7, which is a number, and an equal sign between them. And if you read it like a sentence, you just say x is equal to 7. It reads just fine. That equal sign is a verb connecting the two nouns. So that's how we construct our mathematical sentences, really, is through equations and inequalities. So other types of equations you might see, I'm just giving you another example: 3x minus 9 equals 82, something like that. And these can get as complicated as we want, really. Inequalities are like equations, except the verbs aren't is equal. They're not is equal. They are things like is less than, or is greater than, or is less than or equal to, or is greater than or equal to. So for example, 5x is less than or equal to 18, something like that. Or negative 3y is greater than 12. So I want to talk about solutions, what a solution is too. A solution is the number or numbers that make an equation or an equality true. So for example, look at the equation 3x equals 12. Well, what this is saying is 3 times some number equals 12. These two sides of this equation are equal. Therefore, 3x is equal to 12. In order to make that a true statement, what does x have to be? Well, that means that x have to be 4, of course. So if I plugged in 4 for x, I would get 3 times 4 equals 12. Yes, that's a true statement. Hooray, right? So 4 is a solution. So x equals 4 is our solution. Same thing for inequalities, except for the solutions for inequalities are sets of numbers. So for something like, well, I'll just give you a simple one: x less than 0, say. The solutions are all negative real numbers, and you could graph that on a number line if you like. But that's the solutions to that inequality. The inequality x is less than or equal to 0, or sorry, is less than 0. So it's all the negative real numbers, everything to the left of 0, basically, on the number line. So there's tons of solutions to inequalities usually. Sometimes there's none, but sometimes there's everything is a solution, but we'll get to that later. So that's just some terminology that I wanted to get out of the way. Let's conceptually look at what we're doing when we're moving from one equation to another. The goal of algebra is to solve an equation. Solving means finding the solution. Finding the solution, or solutions, there might be more than one. Finding the solutions to an equation. How do we do that? Well, we basically start with an equation and we convert to an equivalent equation, going by steps. And I'll just show you an example just to give you an idea. So, and if you can follow this, then you're ahead of the game, so that's fine. Say I have 3x minus 4 equals 9, say. Well, I can convert this to an equivalent equation by essentially doing the same thing to both sides. If I do the same thing to both sides, say adding 4 to both sides, then it's not going to change the actual truth value of the equation. The equation will the resulting equation will still have the same solutions. It will, because I haven't really changed anything. I've kept the balance. That's really what algebra means. It means keeping the balance. So what this results in is 3x equals 13. Well, now I can do something else to both sides. So, and notice how I'm kind of lining up these equal signs just to keep things organized. So it's implied that I'm going from this equation to the second equation by adding 4 to both sides. And I'm being really verbose here just so we're all on kind of same page of how the process works. It's important to understand the process so that if your equations get kind of nasty, you can go back to basics. Like, well, I know I can do this to both sides, or I know I can do a certain number of things to move from one equation to the next. And the goal is to get your equation to a simpler form so that you can just read off the answer, read off the solution. So 3x equals 13 has the same solution as 3x minus 4. Well, what would that be? Well, I could divide both sides by 3 or multiply by 1/3, either way, and you get x equals 13 thirds. So now just went from one equation to the next, and I did it in a specific way so that I would be left with x equals a number. Well, that's the solution. That's the solution to the original equation, and you can check that. You can plug that into the original equation. If I plug that x, if this is x here, if I plug 13 thirds in for that and subtract 4, I darn well better get 9. Otherwise, I made a mistake somewhere, right? So 3 times 13 thirds, 13 over 3 times 3 is 13. 13 minus 4, oops, let me do that one again. 13 minus 4 is 9. Well, hey, that checks out. So that is a true statement. So 13 thirds is indeed the solution. But anyway, I just want to show you a quick example of that. There's a couple ways to convert to move from one equation to the next. One way is what I just showed you, basically doing the same thing to both sides. Another thing you can do is you can simplify expressions on either side as well. So if I have something, an obvious thing here is like, I'll just start a new equation here. What if I have x equals 7 minus 9, say? Well, I'm not going to do the same thing to both sides. All I really need to do is simplify that expression. So I don't have to do anything to both sides here. I just have to simplify one side. So simplifying that, you get x equals -2. And you can get more and more complicated with these, but you can simplify each side. And I'll give you some examples of this. So you could simplify either side. So if I have something like this, 7x plus 3x equals 8, well, I could simplify this side too, since I can combine those like terms. 7x plus 3x, 10x equals 8. And then I can continue from there, dividing both sides by 10 or multiplying both sides by 1/10. Another way to simplify, you'll see this a lot. You may see something in parentheses like this, say 4 times x minus 5 equals 10. Well, I can do stuff to both sides, but it's not a bad idea to simplify this first. Well, you simplify that using the distributive law, 4x minus 20 equals 10. And then I can proceed from there, adding 20 to both sides and then dividing by 4. Generally, you always get the term with the variable by itself first, and then you divide by the number that's on that variable. So what I would do first is add 20 to both sides, and then that would leave me with 4x equals 30, and then I would divide by 4. Why do it that way? So x is 15 halves. Again, I'm simplifying 30/4, just that expression, down to 15 halves. I'm not going to write it as a mixed number, that's not necessary. This 15 halves is a perfectly cromulent number. So, what, why would I do adding the 20 first before dividing by 4? I could technically do, it's perfectly legal to divide both sides by 4 at the very beginning, or here. It's perfectly legal to divide by 4 here. But the problem is, if you divide by 4, what happens? Say I've got 4x minus 20 equals 10. If I divide by 4, which is essentially the same as multiplying by a fourth, okay, well, I get 10 times a fourth over here, so that's 10/4. I'll just leave it unsimplified for the moment. Well, this 1/4 distributes. Unfortunately, it works out really nice here because it's x. 1/4 times 4x is x. 1/4 times negative 20 is negative 5. But the problem we get here is this is 10/4 or 5 halves. Now I have to add 5 to both sides, and that's fine. But then I got to figure out 10/4 plus 5. It's generally, you introduce some unnecessary fractions, because imagine if this weren't 20, imagine it was like 17 or something. Then you'd have this 17/4 thing to deal with, and it potentially could. It's just you can do it that way, but you're going to create a little bit more of a hassle doing it that way. It's generally best to get the term with the variable by itself first, and then once you have that term by itself, then divide by 4. Now this is just for what we call linear equations where there's no no powers on x, no squareds or cubes or anything, no higher powers. This is all linear stuff. I've basically gone through simplifying. You can simplify one side, and also you can do stuff to both sides. Both of those are good legal moves to move from one equation to the next. And the goal is always to keep moving the equation to a place where it's more simple. And obviously I could take this 15 halves and plug it into the original equation in for x, and I should get a true statement. Anything you do to one side, if you do something to one side, generally you have to do it to the other. Unless you're just, again, simplifying something, reducing something, or distributing, that's fine. That's just rewriting one side in a different way. I think that's about it. I think we can stop there for now, and I'll make another video here with some examples.